So what do we have? The overview. We have found these elementary particles so far. The up quark, the down quark, the strange quark, the electron, the muon, and the electron neutrino. With these masses in the now common unit. We call these particles quarks. They have a color charge, and we call these particles leptons. They don't have a color charge, it's just named. Lepton basically means a light particle. Okay, they are light particles. In the years after that, in the 70s mainly, but up until 95, they found the rest of this scheme. It looks like this. So now we have a charge, a charm quark, a top quark, a bottom quark. You see this is a very heavy quark. We have a tauon, which is basically a very heavy electron. And we have these three neutrinos belonging to the electron, muon, and the tauon. So as you can see, they are ordered in 3 generations, 1, 2, and 3, and the generations get heavier, right? And it stops here. There's not a 4th generation. The theory sort of tells you that there can't be a 4th. Also, these are very heavy particles. The top quark hasn't been directly observed because it's so heavy, it's very unstable, it really decays so fast that it can't really travel towards a detector. So, of course, if it travels almost at light speed, but it exists such a short time, then it can't travel a couple of millimeters even. So you can't hit it, let it hit the detector. So what you do is basically you look at the decay products and then work backwards. And that happened in 95. So they found the last quark, the top quark, very heavy one. And of course, these 12 particles, we can also have the antiparticles. Okay, so these are the elementary particles. And now, if we look at the other interactions that we have, because this is a strong interaction to stick them together, these quarks, we have the beta decay. So now we know it's this neutrino here. And now we think of it like this. So this is a neutron with the 3 quarks. Basically, one quark, the down quark here, changes into an up quark. And this change can only come about with the weak interaction. So that's a different type of interaction. The strong interaction glues quarks together, but it doesn't change the color of the core, basically. But here you can, the flavor of the quark. So basically this changes the down quark into an up quark. This particle is called the W, or minus boson, it's just a name. And out comes this electron and the neutrino. So now we know what happens in between these two sets, these 2 points. There's also something called the Higgs field, with the familiar Higgs boson, and that's basically describes how particles acquire mass. So we have this set of particles that are force carriers, and the masses are in giga electron volts, so 1,000 times bigger. So these are really heavy particles, and they describe how forces work at a distance. Now the strong interaction and the electromagnetic have massless particles. This is the gluon, this is the photon, this is the zero charged weak boson, and then we have the charged particles here. So these are all the particles that describe matter and their interactions. And as you can see, it leads to a lot of Nobel Prizes, all this particle research. So basically, we can be happy now. We can describe matter and how it acts together. Except that there are many questions left. Why is there much less antimatter in the universe? What is dark matter? Basically, what is dark energy? How did inflation work in the universe? There are many questions left, but this model is very precise. They can make predictions. In chemistry, you think that something is significant if you have a 3 sigma detection. 3 sigma detection roughly means that it's less than 1 in 10, well, less than 0.1% chance that something is wrong. In physics, we say it's a significant discovery if it's at 5 sigma. So that's 1 in a 3.5 million chance that something is wrong. The dipole moment, the magnetic moment of an electron has been measured at 7 sigma. That's a 1 in 1 trillion chance that something is wrong. So, and it's exactly the number that the standard model predicts. So the standard model has been tested in an insanely precise way, and it's completely fits everything that we've seen before. So it is very correct, but it's not complete. this was my talk. Thank you very much. If you want to read some books about it, I have some Dutch books that I really would like to recommend, from basically easy to slightly harder, but there are many books also in English if you want to read about them. So feel free to look up some of those books.